Thank you for joining the November 2022 edition of the 3M Healthcare Academy. Our topic today is Innovations in Steam Sterilization, Leveraging Evidence and Technologies for Safe Load Release. I am Fernando Malgueiro, Medical Education Manager for 3M Medical Solutions Division, and I will be hosting this webinar. Before we get started, let's go to the following disclaimer. The content of this webinar is based on current United States information, including regulations, standards, and guidelines as of September 1st, 2022. Requirements in other countries may be different and US guidance may change in the future. Always consult product instructions for use and follow local laws and regulations. This presentation contains an overview of general information and should be relied upon in isolation to make specific decisions. Today's webinar will be presented by Dr. Paulo Laranjeira. Dr. Laranjeira has 25 years of experience as a process development and qualification professional for sterilization, using saturated steam, hydrogen peroxide, and ethylene oxide in the pharmaceutical, medical device, and healthcare areas. He conducted many investigations with biological and chemical indicators and with different sterile barrier systems, with the findings published in journals. He has authored book chapters, technical documents, and white papers on topics related to sterilization and decontamination and process. Dr. Laranjeira is currently a full-time contractor with the US FDA and invited professor at postgraduate schools on equipment qualification and monitoring for the pharmaceutical and healthcare market. He has also shared his knowledge by lecturing in Congress and symposiums. With that, I would like to welcome our speaker, Dr. Paulo Laranjeira. Please take away.
Good afternoon, everyone. Thank you, Fernando. Thank you, 3M, for inviting me for this presentation. Today, we will be talking about a topic that is part of my research, part of my consulting, and part of my passion. Sterilization is a topic that does have history. Especially steam sterilization was something that was developed in 1880. So we do have a lot of good, solid evidence to use steam sterilization. But as you see in the topic, we do have, and I called it innovations, but it's not innovations to steam sterilization, but it's innovations applied to steam sterilization that were already required since the Red Book of Perkins, where we had already some or a lot of information related to what I'm going to be presenting today. But at that time, the load release related to this steam sterilization requirements were not well designed. And as we evolved and more evidence were produced through scientific papers published in peer-reviewed magazines, we see that today we need to address these characteristics of the steam sterilization, be aware of them. You know, we are going to be seeing a lot of sterilizer manufacturers offering new monitoring devices attached to their device, to their equipment. We are going to see new process challenge devices, and they are related to these innovation phase of steam sterilization related to safe load release. So today, what I'm going to cover, I'm going to discuss about the different saturated steam sterilization applications, and this is important. And I want you all to step back from what you do on your daily basis, because we believe that the sterilizer that we use are only there or only applies to what we do on a daily basis. And that is not true. Steam sterilization is used in many segments. It's even used in tire manufacturing. So let's today take a step back, try to understand the sterilization process as a whole, to understand how we need to implement or understand actually these new innovations and how to safely release our loads. The second item is to identify the requirements for cycle monitoring, how we are going to monitor our sterilization cycles to make sure at the end of the sterilization I can safely release my load. And the hot topic is always related to fast and reliable sterilized cycle release. How can I safely release in a fast process my sterilized load? And here is where we need to address this specifications that we have with Steam to understand how to move forward with my safe release. So what we see today as sterilization, and I have a couple pictures here, steam sterilization, right? We have steam sterilization of liquids, for instance. This is well seen in the industry, especially in the pharmaceutical industry or in the labs of those industries where they have to prepare culture media. It is a specific cycle, and most of the information that you see today is related, for the industry, is related to speed up this process. Then we have what we see in hospitals, which is the sterilization of reprocessed medical devices. Definitely the steam sterilization is a technique that is used globally. Everyone, every country, every hospital has a steam sterilizer. There is no other method in volume used globally. And in the industry, we see the same. We do have ethylene oxide and low temperature sterilization present for, especially for medical devices. But we do have some restrictions now with fugitive emissions, and we're probably going to see some changes in the near future. But steam sterilization is used a lot for pharmaceuticals sterilization, where the ethylene oxide is not used. Then the question is, when you look into a sterilizer, they are basically the same. So the release, it's a printout where you're going to have all the information on the conditioning, on the exposure, and then on the drying phase. Then we are going to have some type of monitoring, cycle quality monitoring, like a biological indicator, chemical indicator. And the question is, can we adopt the same method, the same load release method to all segments, to all areas where steam sterilization is used today? So let's take a look into what we have as examples for the industry. Let's look into the industry, and these are some pictures taken from loads that are processed in the industry. So if you look into the requirements, they need to have air removal, which is what we see in hospital. They need to have a thermal uniformity during the exposure, same requirement. They have to have vacuum-assisted drying phase for dry loads, so the drying phase is the same requirement. And at the end of the cycle, the load needs to be dry. So those requirements for the industry and for the healthcare area are identical. Now, here's another example of load. So just to give you an idea of how many different loading configurations. So for instance, here I have a filters being sterilized. Here are manufacturing components, another manufacturing component, clothes. another filters, if another accessories. So they do have a lot of different cycles for surface and density. It's amazing how much a steam sterilizer is capable to sterilize. Not only our devices, but it can sterilize many different products. Now, liquid. Liquid is something that we don't see much in the healthcare area. Some countries, they do have liquid sterilization, but it's not a common process. But the requirements are air removal, because everybody knows, right? I cannot have air inside of the chamber. I need to remove it. I have to have a thermal uniformity during exposure. At the end of the cycle, it cannot be a fast vacuum like we see in our loads. And the reason for that is that, let's look into a glass of water, right? So if I heat up this water, if it is not covered, it is going to, when it reaches the boiling point, it's going to go over, right? It's going to lose water over the top, right? So what we have in the industry and what you're seeing here, you have flasks that are closed. So if in the drying phase, I take out the steam too fast, I'm going to have all these caps popping up because I have a lot of pressure inside of the container. Now, if I have a slow exhaust, I will maintain the steam pressure over the liquid. So even though the liquid is at boiling point, it will not boil out because I have the steam over it. So this is how in the industry, in the pharmaceutical industry especially, they sterilize liquid, but they have to have a gravity exhaust. Cannot be a fast exhaust like we see in the healthcare area. And for the low dryness, there is no requirement, because for liquid, steam is going to get in contact with the surface of the vials or the flask, and is going to condensate on the outside, but the inner part, it doesn't matter. Because the inner part, the heat, once again, my glass of water, the heat is going to come and get in contact with the surface of the glass. It's going to condensate, but my product is what is inside the glass. So it doesn't matter if I have a condensate at the end of the cycle. And I am going to have a lot of condensate in a liquid cycle because the amount of energy that I need to heat up liquid, it's a lot more than a surface sterilization of a medical device. If I have a medical device, the surface sterilization of a medical device is just on the surface. For liquid, I need to heat up all the liquid. So steam is going to get in contact with the liquid, is going to be changing temperature, is going to be warmer than the liquid, then I'm going to have more condensate. Great. So here is how they control it. This is a different way. You probably, if you haven't heard, they do have a load sensor in the sterilizer, in the steam sterilizer for liquid sterilization. So for them to monitor the temperature inside of the liquid, they have a sensor that goes inside of a reference vial. And when the sensor reaches the temperature, or actually this sensor is used to calculate the lethality, then the whole cycle is actually controlled by this load sensor. So here you see more of liquid sterilization using a load sensor. We don't need to have that in the healthcare area because we are sterilizing surface. So even if you have density, it's nothing compared to liquid. So what we have in the drain can be used as a reference for the temperature, and you're going to discuss a little bit more further in the presentation. Another use of steam sterilization is what we call either water spray or water immersion cycles. You're going to have vials with either a shower of steam from the top through them, or this steam is going, this chamber is going to be filled with water, and it can be 3/4, half, doesn't matter, it depends on the cycle development, and you're going to have water immersion cycles. And the products are going to be sterilized in that manner. Normally you see that when you have plastic vials, because the plastic does not support the pressure oscillation. So if I have the flask in water or a shower, a spray cycle, it will not deform the vial. Okay, now let's look into what we have in hospitals. So as you see from what I showed in the industry to our reality in the healthcare, they are totally different. For healthcare, we have different loads being processed at the same time. We have different sterile barriers. We have different density materials that do create more condensate. So we have a different approach on how to control the cycle. And this is not seen in the industry. The industry does not have the same situation that we have in hospitals, in the healthcare settings. Now, sterilization cycle phases. Everybody knows the three main phases of the sterilization cycle. And normally what we see on key points are instructions for use. We must follow the instructions for use from the manufacturer of the sterilizer, from the manufacturer of the medical device, from the manufacturer of the sterile barrier, and the manufacturer of the quality cycle monitoring devices, like biological indicators, chemical indicators. We cannot have wet loads at the end of the cycle. And here I'm going to add the two new requirements that we need moving forward. We need to start studying them, understand what they are, and in the near future, we're going to have more devices addressing them, which is non-condensable gases and superheated steam. These two new topics, which is the innovation of measurement for safety load release, we will need to understand what they are, and the market is working to bring more solutions. As we speak today, we are having a world conference in Barcelona, where another colleague of mine presented his research on process challenge devices to monitor non-condensable gases. And his findings were really interesting based on the current process challenge devices that we have. And probably his research is going to be used to support the required changes in the standards and also in the requirements for our daily cycle monitoring. So let's look into the difference between our healthcare sterilizers and our industrial sterilizers. The conditioning phase, which is used to prepare the load for the steam that is being injected for the exposure phase. In other words, during the conditioning phase, I'm going to remove air, inject steam, so I'm going to be heating up the instruments, removing the remaining air, and then evaporate the condensate, inject steam again to keep warming up the device, removing the condensate that was formed, injecting steam again, and then to warm up the device, removing the remaining condensate, then I'm going to go up until I reach the exposure phase. So when we talked about conditioning is, like I said, in the first two pulses are removal, but on all positive pulses, medical device surface warming, and this is to reduce the amount of condensate that is formed between the device and when steam gets in contact with the device. And then the last two pulses are there to evaporate that condensate, because I cannot go to the exposure phase with water inside of my package. So that water, that condensate, has to evaporate. And during the conditioning phase, I have my vacuum pump pulling all the condensate from, all the vaporized condensate from the side of the chamber. So that's the conditioning phase. Then, once I reach the ideal point where I have my medical device at that temperature, equal or close to the steam temperature, I start my exposure phase, which has a strict time and temperature. And then after the exposure phase, I go into the drying phase, which I only control time. So in the healthcare settings, I can change. The only variables that I can change are exposure time. It's not drying anymore. Okay, yes. Exposure time, temperature, and then drying time. Those are the only three variables that a healthcare sterilizer can have the set points changed or adjust. For this, let's call it the scientific sterilizer, which is used in the industry, the conditioning phase, I can choose the quantity of pulses that I have, the level, if I want a short or a deeper vacuum, come up time. How much time would it take from the last vacuum pulse to the beginning of the exposure phase? This is the come up time. In the scientific sterilizer, I can adjust that. Exposure, like the healthcare equipment, I can adjust the time and also can adjust the temperature. But in the industry, I can adjust the offset, the variation of temperature, because temperature, what you see on the display, if you have 275 over there or 270, the equipment is not going to run 270 the whole cycle. It's going to have a variation from 270 to 273, 271. And this offset, how much it can vary in the industry, they can adjust it. And for the drying phase, they can adjust the time, like we can in the healthcare area, but they also can choose the vacuum level, how deep. They can have a deeper vacuum, or they can have a shorter vacuum. And they can have pulses of air added during the vacuum phase to improve the drying of the load. Some healthcare sterilizers already offer that configuration. Newer equipment, you're probably going to start seeing it. And what this pulse of air or even steam depends on the manufacturer of the equipment. What it does, when we bring down the vacuum, what happens is we have the jacket at a higher temperature, probably above 270 Fahrenheit, if it's a 270 Fahrenheit sterilization cycle. And when I do the vacuum, if I have water in there, I'm changing the boiling point of the water. But the temperature change from the walls of the sterilizers to the device in the middle is not homogeneous, because in vacuum I have a poor temperature conductivity. So what the manufacturer of sterilizer found out is that if they bring this temperature, this pressure up, injecting either steam or air inside of the chamber and bringing it down, allows the temperature from the jacket to get in contact with those condensates faster, and then when they do the vacuum again, it evaporates the condensate. For the conditioning phase, we do have, for the healthcare settings, pre-configured conditioning phases that we cannot change. but there are 3 of them. They are standardized, and Boydics are challenged to those curves to make sure they can capture the performance of the cycle, the performance of the pump removing the air and steam going to the chamber. So we have the subatmospheric. So here we have ambient pressure, and all the pulses are negative. Transatmospheric, which is the most common one. You have here ambient pressure, then we have negative, positives, negatives, and positive pulses, so forth and so on. And we might have some positive pulses afterwards, might, okay? And then the superatmospheric, you're going to have all negative pulse. So here is the atmospheric pressure, ambient pressure. Then we're going to have the initial vacuum pulses only on the negative side of the phase, of the conditioning phase. And then afterwards, all the other pulses are going to be positive, okay? Oh, what did I do here? Oh, here it is. So let's look back into what's the evolution of the sterilizers of the cycle controls that we have since Chandler, since 1880. In dry loads, what we have, comparing the Chandler autoclave, which was a gravitational sterilization equipment, we had a slow come up where air was being pushed out until it reached the temperature. So we had steam going to the chamber and pushing air out. And then once all air was removed, we started the exposure phase, which was not homogeneous. And then at the end, we had a gravitational steam remover from the chamber. If the addition of a vacuum pump, we are able to do the conditioning pulses. Built-in steam generator. So the previous autoclave, Chandler autoclave, the water was added inside of the chamber and heated inside of the chamber and converted into steam. That created a very unstable steam temperature. So a built-in steam generator outside of the chamber of the sterilizer, or even though a external steam source would create a better steam exposure phase. And with the jacket, I would not have that condensate forming because of the steam getting contact with the jacket like I had in the Chamberlain autoclave. And the automated control allowed us to have a faster, more reliable cycle than the initial sterilization cycle. For the liquid that we see in the industry, so the liquid, like I mentioned, is a bit different because we cannot have vacuum added. So the pump during the conditioning phase, we had steam going inside of the chamber, and the vacuum pump is used to have a controlled steam removal and air without creating a vacuum, a negative pulse, but also forcing the air to be removed from the chamber and then going to the exposure phase. The same here, if the built-in steam generator and jacket, we had a better exposure phase, different than what we had with the Chandler autoclave. And then the exhaust or the drying phase was a very slow one. To give you an idea, sometimes this drying phase for liquids can last over 4 hours. So in industrial scientific sterilizer, they have a very, very long cycle. You can see and you can hear about vacuum pump added with a compressed air. So you can create a vacuum at the end of the cycle for liquid. And for that, you need to have compressed air inserted inside of the chamber. And what the compressed air would do, and this is a clean, sterile air, it goes inside of the chamber, and as I remove steam, it replaces with air, maintaining the pressure over the liquid. By doing that, I can remove the steam faster, and I have a faster cool down cycle. We keep doing this. Let me move it to the other side. Okay. So when we are talking about conditioning phase, and this is where we need to start looking to the critical points of the conditioning phase, is in your sterilizer, in your healthcare sterilizer, your cycle is controlled by a sensor at the drain. Okay? Let me try to use the color here because I have those red in there. Perfect. Let's use this one. So you have a sensor placed at the drain, which is known to be the coldest spot in the chamber, that is controlling the cycle. So this sensor, after the conditioning phase, I have the conditioning phase here, is going to show this temperature to you or to the controller, right? You're going to be seeing this temperature on the display. The question is, what is happening in your load? This is the critical part. And this is where we need to improve the monitoring and how we release our loads. If I have non-condensable gases, and non-condensable gases are any gas that will not condensate during the conditioning phase. So it's a gas that does not condensate. So during the conditioning phase, I cannot remove it. So this air is going to be inside of the chamber. And because this air is colder than steam, it's going to get closer to the medical devices. And the temperature of the medical device is going to be lower than the temperature that we see in the display if I have non-condensable gases. So this is a risk for a failed cycle, because if I have non-condensable gases inside of my chamber, my control sensor is going to show that the temperature was reached, but in reality, my temperature inside of the load never, or basically reached the sterilization, or never reaches the sterilization temperature. So this is the first critical characteristic that we have, and is related to non-condensable gases. When we use process challenge devices, those process challenge devices, they will monitor presence, those density process challenge devices, they will monitor the presence of non-condensable gases. But we have to be careful how our sterilizers are controlled. We have the process challenge devices with the CIs developed according to the red cycle curve that we are seeing here. But when we go into a healthcare site, sometimes we find the cycle running according to this actual graph in green that I have here. And the difference between them is that the last vacuum point to the initial exposure has a lag, basically, of, if each square is 1 minute, we have a lag of 4 minutes of additional high exposure. Let's say that this is 250. Ugh, terrible. Let's take that writing out. So let's say that we have 350 here in this line. We are going to have an additional 4 minutes of high temperature exposed to those chemical indicators inside of the process challenge device, added to the 4 minutes of exposure. So we are going to have 8 minutes of exposure on top of the CIs. And this is something that is not standardized and is critical for our load monitoring. If we have long come-up curves, we probably will have CIs inside of PCDs not detecting correctly a failed cycle. So we have to be careful with a long come-up curve, and the come-up curve is measured from the last minute, from the last pulse, when the exposure starts. So if you look into your printout from your sterilizer, and if you have your last vacuum pulse ending, let's say moment 0, and 2 to 3 minutes afterwards it starts exposure, that's a perfect come-up curve. But if from this minimal, the last pulse, to the initial exposure goes over 5 minutes, and I have seen 10, 12, 18, that means that you have a long come-up curve, and all CIs inside of your sterilizer are going to show approved cycle. Doesn't matter if they are in PCDs or if they are inside of loads, it doesn't matter. It's going to show approved cycle. So this is something that we do have a PCD that will detect non-condensable gases, but if the come-up curve is not correctly configured, we are going to have a failed approved cycle. When you look into the exposure, so we are talking about the condition, let's look into the exposure phase. The exposure phase is controlled, is standardized. Manufacturers have to follow specifications for these criteria. So the lowest temperature to reach sterilization temperature can delay up to 15 seconds. And the fastest one can go over 60 seconds, and then getting to a temperature band of 3 kelvins for the remaining of the holding time. And this is for small loads configurations, which is where we see that happening. For larger ones, we don't have this situation, so they don't have that criteria. So full load configuration don't have that, but for small loads, we have that criteria. But even though it doesn't matter, this is just to show to you that all the standards that we have today only focus on the exposure phase. They do not, besides those 3 standardized conditioning phases that I showed, they do not have any criteria at all for duration, variations, so forth, so on. Okay? And then for the last part of the cycle, for the dry loads, the only thing that we have is that at the end, all the loads have to be dry. I cannot have water inside of my package. Liquid, like I mentioned, this is just to show to you how this is the sensor inside of the load, this sensor here. So even though the equipment, the drain, reaches the sterilization temperature, the temperature on the liquid takes a while to heat up, right? And then what they use is the calculation of F0, or lethality, because they never reach, sometimes they never reach temperature. So that's how they do for liquid sterilization in the industry. Okay, now let's look into cycle monitor and how we're going to release with all this information that I presented to you. So the first part that I want to talk is related to the physical parameters. When we talk physical parameters, we're probably going to hear about parametric release. If you haven't heard about parametric release is based on what we have on our cycle printout. The cycle printout that we have in a healthcare facility, and that's why we need to make sure when you read a recommendation and you see someone moving to a new, faster process release or sterilization cycle release, we need to make sure what is being addressed and what is being monitored. So for industry, by having a sensor on the load, it's easier for them to adopt physical parameters and release the load based on these parameters. But for us in the healthcare area, we have a load, or we have a temperature sensor not placed inside of the load. So what we have from our printout is what we are measuring at the drain. And at the drain is where we capture all this information: time, temperature, and pressure. We do not have, for physical parameters, the measurement of non-condensable gases and superheated steam. These two characteristics of the steam that have been demonstrated in the current and recent evidence to be critical to the sterilizers are not measured by current physical parameters that we have in our sterilizers. So for that, and before going to the chemical, when you look into the printout, this is important. So when you look into the printout of the equipment, it does bring you a lot of value to reduce your load. It needs to be used with the other indicators, with the other chemical and biological indicators. But when you look into the printout, it is important, let me change color here, not only to look into the exposure phase, but to make sure, and you have to compare all your cycles, that the conditioning phase, like the vacuum pulses, the positive pulses, they're being at the same levels for every single load. That the exposure had temperature variations within the limits, so minimum and maximum temperature, minimum and maximum pressure, and the time is correct. And the drying phase, that the vacuum pulse, or the last point here, was reached with the vacuum pump, because when we have the vacuum at that point, it's you only reach that point at the beginning of the drying phase, because then after that we are going to be sending too much condensate through the vacuum pump that it's going to heat up and it's going to lose its efficiency. So that's why you see in a graph, you're always going to see that the first pulse, or when we start the drying phase, is going to be the deepest point of the cycle, but during the drying phase, that point rises, and that's related to inefficiency or reduction of efficiency, vacuum efficiency, because of heat and excessive condensate formation evaporation during the cycle. For the physical parameters, they use, and if someone, I know it's when you talk about lethality, and everybody wants to run away from it because it's like they start showing a formula. So what I want to show to you how the lethality is calculated for a parametric release. They use this formula, and this formula is based on temperature and time variation, right? So like I showed you, this temperature that is measured, that is used in the lethality, is measured at the drain. It's not actually what I have inside of my package. So when we look into a lethality for cycle parametric release, for healthcare settings is not applicable. And also we don't see any variables in this formula that looks into non-condensable gas and superheated steam. For the biologicals that are used to monitor and control the cycle, we have, in theory, a 12 log reduction. So we start in 1 million, and you're going to reach 10 to the minus 6. So the red one is the theory, right? But all the biological indicators that we have, and this is because a spore from a microorganism is going to be just like us. We are not identical to each other. So we have different sizes, we have different, the spores are different. So we have to have more spores to have more resistance to the process or less resistance to the process. So what we see in the market are actual biological indicators that are more resistant than the theoretical value. So when we adopt a parametric release based on lethality, if a theoretical value is used, the BIs that are used to monitor the cycle might have positives because the cycle is too short. I might have BIs showing positive if my cycle falls into this region here. So that is why we cannot adopt parametric release the way we have our equipments today. So for us to release a load in a healthcare setting, we need to determine, we need to make sure that the time of the exposure occurred, that the temperature was present, the steam was at that quality that it does not, is not superheated, nor doesn't have too much condensate, and we have a 12 log reduction. And we cannot have non-condensable gases. And I added this non-condensable gases here slide because I want to talk about the most common source of non-condensable gases, which is water underneath the sterilizer. Actually, it's not the source, but is the cause, right? So when we see water underneath our sterilizer, if you go in the technical area and you see water underneath the sterilizer, that means that I have steam leaking. If I have steam leaking during the cycle, the leakage converts into an air inlet into the chamber, and I will have air going into the chamber during the sterilization phase. And during the sterilization phase, I don't have my vacuum pump, and everything that goes inside of the chamber, it stays inside of the chamber. Because of the Dalton law, there is no way that the pressure sensor can see if the gas that is inside of the chamber is steam or air. I'm going to have non-condensable gases present during the cycle, and I'm going to have, I'm not going to reach the sterilization level that is required, the sterility assurance level of a 12 logs reduction. So non-condensable gases, they can be measured. Today, the requirements is to measure at installation of the equipment. So here is a kit that is specified at the EN285, which is the standard for large sterilizer manufacturers. It's a European standard. And here is the kit that I built myself, measuring non-condensable gases going to a steam generator. So it can be measured at installation and can be measured whenever you guys want. Dryness of the stream also can be measured, also needs to be assessed. And the reason for that is when we talk about steam, that we want to go from liquid to the gaseous phase, there is a difference between liquid changing to a gaseous solution, and then 100% exempt of condensate, and then superheated steam. In this case, when you look into the cycle, the way that we have the cycle controlled, the equipment is using temperature from the drain, pressure from the chamber, measure the chamber, look into a table, and this table says that if the temperature and pressure are identical, I have saturated steam. But inside of the chamber, you do not know if this saturated, so here you have 270 Fahrenheit at a 43 psi pressure, 3 bar, and the equipment is looking to only pressure and temperature, but we do not know if it is at point B or point C. If it is at point B, I'm going to have less energy being delivered to the sterilization, and if it is at point C, I would have the correct amount of energy transferred to the sterilization cycle. And so today, the equipment cannot measure the stream dryness also. We can measure the EN285, thus shows how to measure it. Here's another measurement that I performed, another kit that I put together based on EN285 to measure that. But what I want to show to you and what I want to bring to you today is that when you look into a sterilization cycle, and we are going to look into literatures, we are going to see a lot of references where we are going to be moving forward. We need to have faster, reliable sterilization cycles cleared in a secure way, right? We need to improve our process. And we are going to see the industry moving into parametric release. And what I want to call out is that for the healthcare settings, parametric release cannot be adopted because we do not have a standardized load. We do not have sensors on the load. We do not have control of non-condensable gases and stream dryness. Therefore, parametric release cannot be adopted in healthcare. Another point is that, like I showed to you, parametric release is going to be based on time and temperature. That's all. That's all they are going to be using. And they are not taking into consideration steam dryness, the energy that I showed you before. So for us, in the healthcare settings, we need to understand that we have two new components that need to be monitored. Our current monitoring devices are capable to detect non-condensable gases, and biological indicators are capable in detecting steam dryness. And if they are used according to the manufacturer's IFU, and if you follow the IFU from the manufacturer of the monitoring devices, the IFU from the sterilizers manufacturer, and the IFU from the device manufacturers, and the IFU from the sterile barrier manufacturer, we are going to be safely monitoring your load and releasing it daily. But moving forward, we need to start looking to these two criteria because they're going to be needed to be monitored. Equipment will need to have some type of a sensor added so we can have that with our physical indicator, with our printouts. So this is everything that I presented to you. As I added references here, all the information. Some of the slides are referenced here, and some of the content that I spoke are referenced in this bibliography and this reference that I gave to you guys. Everything is pretty much new. New research, there are more coming out. We have more scientific papers that will be published in 2023, and hopefully the new standards will address these new changes and also help us improve our process. Okay, that's all I had for you today, so we can move forward into the Q&A. Fernando, back to you.
Thank you for the great presentation, Dr. Laranjeira. This concludes the educational portion of this webinar, and we will now move to answer some of the questions that came through during the presentation. Let's move to the Q&A session. What is the main cause of wet loads?
There are many causes of wet loads. We don't have a main cause. We have to do, when we have wet loads, we have to do a assessment to make sure to determine the root cause of that wet pack. But I would say the most critical component of wet packs today are excessive loading. The mass, when we load the carts, if we overload them, because we as human beings, when you look into a chamber and you see space, you say, oh, let's use that space and put more product in that chamber. Unfortunately, we have to control mass, and sometimes mass does not cover all the space available, but goes over the maximum mass that the manufacturer of the sterilizer configured the equipment to work with. So if you overload it in mass, you're going to have wet packs. And the second one is the materials that are used to build medical devices. We are seeing a lot of non-metallic materials being used in the manufacture of medical devices, and those non-metallics, they condensate a lot. So those are the two main reasons. But if you have wet packs, please focus on the root cause analysis and really do a thorough assessment, because sometimes it's just a simple loading error.
Thank you. And the second part of this question is, and what to do with the wet packs? Can they be released?
These questions, we see it globally. Okay, so let's do a critical analysis, right? That condensate that you are seeing came from a source that is the steam, right? The condensate did not come from outside of the chamber. It was produced inside of the chamber. So that condensate does not have any contaminant, that's for sure. There is no question on the condensate. The problem is that condensate is showing you that something happened during your cycle. And like I showed, the equipment does not control all the critical variables. We need to control other variables than only the temperature in the drain and the pressure of the chamber. So that condensate is showing you that something happened that was not shown in the printout, nor the chemical and biological indicators were able to detect it. So it's not a problem of a wet pack being used, it's the problem behind the wet pack. The wet pack is showing you that something happened and you do not know what happened. And it might be that that device did not reach temperature for the amount of time that was required for the sterilization. For that reason, and I always reference ST79, and I think the approach that they have, it's a good approach. If you have wet pack in one single item, you're going to reprocess that item, and if you have more than one, then it's a problem of the cycle. The whole loads need to be reprocessed. So forget about the wet. The wet is not the problem. We can discuss it about storage afterwards, if it is going to be exposed, that water is going to be, you're going to have growth, yes, after sterilization. But we are talking about clearing after the process, right? I see it wet. What should I do? And this is what my assessment is based on.
Thank you, Dr. Laranjeira. You mentioned that CIs may not detect the failure in the exposure phase. Is BI included?
BIs, based on current research, BIs are still the best evidence for a cycle monitoring. If I have non-condensable gases, if I have superheated steam, or if I have a steam that does not have enough energy, my BI will detect it. I keep saying that sometimes BI are looked at it because they only measure the first part of the overkill curve, which is the kill part from 1 million to 0. But actually, that's just the curve used for the lethality. The BI, the spores per se, they have a behavior through the process that if steam is superheated, for instance, it will not die. And you have a positive result. We'll show that you have a failed cycle. So BIs are still a stronger monitoring device today.
Awesome, thank you. We are reaching the top of the hour, but I will ask you one more question as we are getting a lot of them, Paulo. How to determine which is the coldest point in the chamber?
The best measuring point to measure the cycle, is that the question?
Yes.
Okay. We currently do not have the habit of doing temperature mapping of a steam sterilizer. And unfortunately, that's the only way for you to study your chamber. Those hospitals that implemented temperature mapping, like Ana Castillo, they do have in her institution, they do monitor the cycles. and it's a voluntary approach, it's not mandatory. But by monitoring, putting thermocouples inside of the chamber, I can see how my equipment behaves and how the load that I place inside of the chamber is behaving during the cycle. That's the only way to determine the points, the critical one, the worst one, the best one, all the points.
Thank you so much. Unfortunately, Paulo, we don't have more time to answer questions. We hope you all had a good time with us today. For more 3M sterilization and cleaning monitoring education, visit Sterile, powered by 3M Healthcare Academy.